All right, let's talk now about current division. All right. Now, we're going to consider a circuit that's really got two resistors in parallel. So here they are. We've got a R1 resistor sitting here, and we've got a R2 resistor over here. All right. This current we're going to call IT, and this current over here we'll call I1. This current over here I'm going to call I2. All right? So let's think about this a little bit here. Let's imagine that we wanted to first find the voltage between here and here. So let's call that voltage, we'll call it VT. How do we do that? Well, I could find the equivalent resistance here, couldn't I? And I could draw a circuit, redraw this, where I've got IT, and I've got my equivalent resistance sitting here. So that's R equivalent, and this voltage would be my VT, and I've got IT flowing, as it were, through that equivalent resistance, okay? So what is that equivalent resistance? Well, that equivalent resistance is simply equal to the parallel combination of those two, which is what? It's R1 times R2 over R1 plus R2. Yep, okay. So my voltage VT then is what? My voltage VT is going to be equal to this IT multiplied by that equivalent resistance. Yep. And so that's IT, which is multiplied by the R1, R2 over the R1 plus R2. Okay? All right, supposing now I want to find that current I1. All right, what's I1? I1 would be equal to what? The voltage across it, yes, there, which is VT, divided by what? The resistance R1. So we have this expression for VT. Let's put that into here, and we can say the current I1 is equal to VT, which is the R1, R2, over R1 plus R2 times what? IT, and that's divided by R1, isn't it? Okay, so what is that equal to? That is equal to, that goes with that is simply equal to R2 over R1 plus R2 times IT, isn't it? All right. So what about the current I2? Well, yes, the current I2 then is equal to what? Well, it is equal to VT divided by R2. What is that equal to? Well, there's my VT. So that is R1, R2 over R1 plus R2, and that's times IT, this time divided by R2. So what is that equal to? Well, that is equal to, this cancels with this, that's equal to what? R1 over R1 plus R2 multiplied by IT. All right, now think about this with me for a moment. What I'm saying, I'm going to recap. What I'm saying is if I want the current I1, so I'm recapping here, I1 is equal to, without going through the derivation here, I1 is equal to, take the opposite resistor, which is what? R2, divide by the sum of the two, which is R1 plus R2, multiplied by the current IT. So if I want the current I2, what am I doing? I take the opposite resistor, because I2 is in here, take the opposite resistor, which is what? R1, divide by the sum of the two, which is R1 plus R2, and multiply it by IT. All right, and you'll see that these relationships are the same as what we derived above, you know, from a first principle point of view. So this is the current divider relationship. It is a useful relationship when you've got two resistors. It's useful to remember this formula when you've got two resistors. Don't try to do it for 3 or more. deal with your problem really from first principles if you've got more than 2 resistors. It's not worth trying to develop another formula for 3. Only use it, the formula approach that is, when you've got 2 resistors. Any more than 2, do it from first principles. All right, let's have a look at this example. What we want to do is find the current I1 and also find the current I2. We've got a current generator sitting over here, okay? So using the current divider relationship, we can say the current I1 is equal to what? Yes, take the opposite resistor, which is what? 3K. Divide by the sum of the 2, which is what? The 3K plus the 6K. And what am I multiplying by? The current, which is this 12 milliamps, okay? If you work that out, this comes out to be 4 milliamps. The I2 current, all right? The current in this branch here. What do? We take the opposite resistor over here, which is 6K, divided by the sum of the 2, which is the 3K plus the 6K, and that's multiplied by that 12 milliamps. And of course, that is equal to 8 milliamps, okay? So, very useful expression to remember when you're dealing with 2 resistors in parallel. Any more than 2 in parallel, resort to a first principle approach.